results with h below x2 alpha, I think. So anyway, we get, by the variant of this result, we get that we understand the divisor correlations for almost all h up to this x to 8 over 33. Well, understanding means that we save some powers of logs. It's quite nice. And another motivation to study these correlations of the divisor function is that they are related to moments of zeta function. So this, if we look at the kth divisor function, then it's related to kth moment of zeta. So if we understood this very, very well, then we could get information about moments of zeta function. So it's interesting to study also these correlations of the divisor function. And I have another theorem which gives us some information about them. Some more information in addition to this, that the variant of the theorem 1 works. With theorem 2, again, give maximentary. And for the divisor function, we can go to much smaller h. So again, it's x less than h. But this time we just request that this h is at least log x to ck for some constant depending only on k. So I should say that for the value of ck, something like 10,000 k log k seems to be certainly acceptable. This is still work in progress, and I guess we can reduce this 10,000 to be something smaller, but we can't get rid of this k log k, and there are good reasons for that. Our method just can't work beyond this k log k range because it's based on looking at divisor function in short intervals, and if we have two short intervals, the oscillation of the size of the divisor function starts to be bad. I mean, then one single term will dominate, and then we are in trouble. So that's why we have to have the range to be at least k log k, and at the moment it's something like 10,000 k log k, but I don't know what it will be eventually be. But anyway, let's just think that it's some constant. Okay, so we get the similar result as there, but for the divisor function. Then the sum of dk n plus a equals to main term times 1 plus e to the power of 1. So I'm not going to discuss the main term in detail, so it's x times some polynomial of degree 2k minus 2, but I'm not discussing it. It doesn't look very nice, but it comes from the main source and we don't have to worry about it too much. But anyway, the point is that we get asymptotic formula for this. This is the main term. I should say it so that nobody thinks it's m times t, so it's main term. Okay, and this holds for all but e to the power of h values h smaller than h. So you can see the difference between the theorem 2 and theorem 1 for the divisor function is that now we have much shorter average. I mean, we can do almost all h in a pretty short range, but what we have to pay for it is that our error terms are bad. I mean, we just have little of 1 instead of log savings, and we only have that the exceptional set is little of h rather than log savings here. So that's the price we have to pay for going into shorter intervals. And unfortunately, that price is so big that we can't travel from here to the von Magnard function. So this doesn't imply anything about the primes because these error terms, or this, in particular this error term is so bad. So we would need to save some logs here in order to get an implication for the von Magnard function. But it's still sort of nice to know that we get for the divisor function, we can get the asymptotics for very short intervals, even though the asymptotics don't imply anything for the von Magnard function and probably don't imply anything about the moment of zeta either. Anyway, we can do it. Okay, so now I've stated two theorems, and I will next start talking about how to prove these theorems. And there are similarities in the proofs and there are differences, but I will start with the general setup, which is same for the both theorems and which is using the circle method. Okay, so what we want to do in both cases, we want to study something like an plus 8, and in our case it's either the Boyd-Magnard function or the divisor function, but for now it doesn't matter what we are studying, but we are studying the correlation of something. And by the circle method, we can write this as the integral from 0 to 1 of some an e alpha n squared e minus alpha. So this integral picks up those n1 and pairs n1 and 2 where n1 minus n2 is this. So just write this condition that write this as n1 and this as n2 and want n1 minus n2 to be a. You can use the circle method in this way, and then we need to analyze this integral, but what helps us is that we only want the result for almost all 8. And the first step, as usual in the circle method, is to split this into major arcs and minor arcs. And we do that first. So we split this into 1. Union of major arcs and minor arcs, and I think my aims look similar, but I don't talk about major arcs, so from now on it will always be little m when I'm talking about something. So if we write this as S alpha, and I just say that we can handle major arcs, so this is the only capital M that will be here. And the major arcs, and they give the main term. And this is a standard thing to do related to distribution in arithmetic progressions and stuff like this, so it's a standard way to handle the major arcs, so we don't have to worry about them, but the point is that we have to worry about the minor arcs. Of course, I haven't yet told you what are the major arcs and what are the minor arcs. So the major arcs are things that are close to a rationally or small denominator as usual, and the minor arcs is the rest, and I think for now we don't have to know anything more about them. So we can get rid of the major arcs and we just have to study the major arcs. So we study this integral over minor arcs. Okay, and because we want the result for almost all 8, we can take a mean of this and sum over 8. Okay, and then we want to get some trivial bounds for this thing in particular, that it's for almost all 8 smaller than the main term, which is of size x times log x to 2k minus 2 in the case of the divisor function. Anyway, we want to study this mean here, and then I have to do a bit of tricks with squaring out and changing orders of summations and summing over 8, and we are getting some gain from the sum over 8. And anyway, doing this, we first end up with something like sum of 1 over 8 and integral of here. So just believe me that this is the case, but you can morally see it if you square this out and you look at, you end up with alpha 1 and alpha 2, and then if you do the H sum first, then it's only bad if alpha 1 minus alpha 2 is small, because otherwise you win from the geometric series here. So that's why I get restrict sort of a S alpha squared with alpha on a short range. But anyway, I don't go into details about this step, but it's quite straightforward, but you have to do it. But yeah, let's just believe that this is true. So this is related to looking at the average of short integrals of this S alpha thing here. And in order to do this, I do sort of a thing that people often do in circle method. I do take a supremum of something, and then I want to apply Parseval or something like this for the rest. So what I do is I take a supremum of this integral out for part of this, and for the rest I keep the average. So what I do is I take this is most supremum of alpha in the Weinmax, this integral say beta alpha smaller than 1 over h of s beta squared d beta. So this is one component here where I have essentially taken the supremum of the I, and then I have found if there is some point on the Weinmax, I just take into effect 1 over h around it. So this is part of the thing, and I have a second power here, so I am allowed to take out any smaller than second power. So let's say I take power delta out there, and then I'm left with the rest of the thing with a smaller power. Except that now I only have 2 minus delta. This guys. So I have taken the supremum of part delta of this, and I have here with 2 minus delta. So here delta is anything between 0 and 2. Okay. And this looks sort of familiar to circle method things that you get these averages of exponential sum, and you have supremum somewhere, and you have a mean somewhere, and then what we want to do next is to estimate the